Hey guys, I'm back with a new video. In this video we'll learn about classification technique and then we will start with logistic regression algorithm. So the topic for this video is classification. So in the previous video we'll learn about the gradient descent algorithm. We'll implement that as well in a later video. If you haven't watched those videos yet, do watch them first, otherwise you will not be able to understand most of the things in this video. From this video onwards, we are starting a new topic, which is classification. We had already discussed in brief in the previous videos that the output variable, which is y that we predict in case of regression, is continuous in nature, and you can easily compute it because it is quantifiable in nature. On the other hand, if I talk about classification, the output variable here in this case is discrete in nature and not continuous. So discrete in nature. So it's a discrete variable. Suppose you are given images of two fruits. So as you can see here, so one is an apple and one is an orange. Okay. So you know the features of these fruits. So you know that apple can be red in color or it can be green in color, and an orange is orange in color. Then both have a round shape, and you need to classify which one is what. So as you can see here, y can take two values here. It can either take an apple, so it can either be an apple, or it can either be an orange. This means that output variable here can take a value from a finite set of values, and in this case this set is apple and orange. Therefore our output variable can only take one of the values from our given set of values. Now let us see how we can solve a classification problem. For now, let us assume y is a discrete variable and can only take values between 0 and 1. So we will have values 0 or 1. So if we have a value of 0.32, say it is 0.32, so it's not possible here in this case because our variable is discrete here. It won't take any value that lies between 0 and 1. It is bound to be either strictly a 0 or a 1, nothing other than that. So what we can do here is that instead of predicting the output variable directly, we can try to predict the probabilities for each of the class. This means that we can predict that what is the probability that a new unforeseen data point, which is this, resides in the class 0 or in class 1. Now again, why are we not using linear regression here, even when we know that the probability variables are continuous in nature? We know from mathematics that the probability value will lie between 0 and 1, both inclusive. And we also know that probability can take any value within this range of 0 to 1, and hence it is continuous in nature. The reason for that is our output variable y is bounded between 0 and 1. So let us understand this in detail. Let us try to use linear regression to understand this. So I will plot the input variable along the x-axis. So input variable x along the x-axis and the output variable along the y-axis. So now let us assume some point density for which y is 0 and y1. So let the point density be something like this. Now let us try to pass a linear regression line through above data. So this is a line that is passing through above data, and the data is confined within the bounds 0 and 1. Now here you can see within the range there are no values that you can make use of because your y cannot be between 0 and 1 because it is a discrete variable. It can be either a 0 or it can either be a 1. Now if we plot the probability along the y-axis, so let me draw a fresh diagram, 0 and 1, and let the y represent probability, and let us our data is something like this. It will not exceed 1. It is confined within the bounds 0 and 1 and pass the regression line. Now if we plot the probability along the y-axis and drawing the regression line passing through this point density, so if we consider the region, let these points be your value where the probability comes out to be 1 and probability comes out to be 0. Okay, so let us define this using some vertical lines. So if we consider the region to the right of this point, so to the right of this point, and to the left of this point. Okay, to the right of this point where p is 1 and to the left of this point where p is 0. Now for all the values that are greater than the x value for this point, so we will have some x value for this point, and all the values that are exceeding the x value of this point, that is to the right of this point, the probability values will be greater than 1, as you can see. So here probability values are represented by this thing, okay, and it is greater than 1. You can see it is overshooting the value of 1. Let me show this. So this is where we have 1 and all the values are going above it if x is greater than this point, this x, okay. And for all the values of x to the left of x value of this point where we are getting p as 0, you can see we are getting negative values for our probability because it is going below 0. The probability values will come out to be negative, which means less than 0. Now, by the definition of probability, that it is a continuous variable and the value for it can never be less than 0 and it can never be greater than 1. So the value for probability must lie between 0 and 1, both inclusive. So this is the main reason why we cannot make use of linear regression. You cannot use this, okay? Now here comes another topic, which is logistic regression, which deals with probabilities and helps in solving classification problems. The word regression in logistic regression comes from the concept that probability is a continuous variable. But how can then logistic regression helps in solving problems on classification? So let me explain this in detail. The logistic regression is a classification algorithm. So in classification problem, you segregate your data in two separate classes. So if we have the case for binary classification, then we separate our data into two classes. So let us discuss in detail about logistic regression. So far, a simple linear regression, we had the equation y is equals to m0 plus m1x. So this was the equation for simple linear regression. For case of multiple linear regression that we had discussed in the previous video, the equation was something like this. So y is equals to m0 plus m1 into x1 plus m2 into, so here also multiplication, m2 into x2 plus m3 into x3 and so on. So let me write down the equation for logistic regression. Now it is of the form, so logistic regression, so this is for multiple linear regression. So logistic regression, the equation is of the form y is equals to a function of m0 plus m1 into x1, so you can directly put this here, plus m2 into x2 and so on. So the function f here is defined as f of b, so we can say f of b as 1 by 1 plus e raised to the power of minus p. So e is your exponential function. So let us use both of above conditions or equations to see how the logistic regression comes out to be. So from this we can get y is equals to 1 upon 1 plus e raised to the power of minus m0 plus m1 into x1 plus m2 into x2 plus dot dot and so on. As a side note, here the input variable x is not linearly related to your output variable y. As in linear regression, this is a bit complex function compared to the one that we had for linear regression, and here y is your estimation probability. So let us understand the shape of logistic regression function. The function is known as your sigmoid function. So it is known as sigmoid function that we had discussed, which is y is equals to 1 by 1 plus e raised to power of minus p. So let me trace a graph for this. Let us take some points along the y-axis. So this has 0, 0.5 and 1. So what you can see from this graph is that we are having bounds of 0 to 1, and the curve looks something like this. So what you can see from this graph is that when your b value, so here we will have b along the x-axis and f of b along the y-axis. So when your b value is tending to plus infinity, the value for your sigmoid function will be 1, as you can see here. So here we will have the value of 1 when your b is tending to infinity or plus infinity. You can see this curve is tending to the value of 1. So the value of fb comes out to be 1 when your b is limiting or it is tending to the value of infinity. But it will never exceed the value of 1, as you can see. So it stays elevated at this value and it will not exceed 1. And to the left of origin, so if we go to the left of origin, as you can see, as the value of b tends to minus infinity, the value of sigmoid function will tend to 0. So it is approaching or it is nearly touching the x-axis. Okay. And to the left of origin, you can see as the value of b is tending to minus infinity, your curve will be nearly touching the x-axis. So it will tend to a value of 0. So your fb will come out to be 0 when your b is tending to minus infinity. Okay. And if your b is 0, fb will be 0.5. In the equation, if you put b as 0, so y when b is 0, you will get 1 upon 1 plus e raised to power of minus 0, which is 1 by 1 plus 1, which is 1 by 2, or you can say 0.5. So we can see well from the graph that the value of sigmoid function will be greater than or equal to 0. So it will always be greater than or equal to 0. Okay, but less than or equals to 1. So if you map this to the probability function, which also lies between 0 and 1 inclusive, you can say that logistic regression resembles more closely to the probability values that we are getting than linear regression. So just like the probability, the sigmoid function will also remain within the bounds of 0 and 1 inclusive. So to conclude, this is a better function that we can make use of to predict probabilities if you compare it with linear regression. So let us understand in context of binary classification how logistic regression can help you in separating your data into classes. So let us again draw the graph for logistic regression on one side of the whiteboard. So it was something like this: 0.5, 0 and 1. So this is where we are getting a value of 1 and this is where we are getting a value of 0. So let me take an example to understand how we can make use of logistic regression for classifying our point density. So let us take two classes. One is represented using asterisk, so this is your class 1. Another is represented using dollar, so class 2. Now let us take x1 input variable along the vertical axis and x2 input variable along the horizontal axis, because we know that we are making use of two classes. So our logistic function will look something like this: y is equals to f of m0 plus m1 into x1 plus m2 into x2. Just this. Okay, so let us say a star are all over here and dollars are all over here. So if we have a new unforeseen data point, say a box, so this is our new unforeseen data point, we have to put it into the right class. The main goal of the classification problem is that you have to place a new point into its right class. So let this point be a box. Okay, so let us go back to the point where we discussed about the sigmoid function. So from that graph you can easily say that, or you can easily deduce that if your b is greater than 0, then f of b, so this was b along the x-axis and fb. If your b is greater than 0, then you can see that your f of b is greater than 0.5. You can clearly see that. and if b is less than 0, then fb is less than 0.5. So if your b is less than 0, fb is less than 1 by 2. If your b is greater than 0, fb is greater than 0.5 or 1 by 2. Okay. And I earlier told you that f represents the probability that you are estimating. So from the two conditions, you can say that if b is greater than 0, then we can say that there are higher chances for the data point to lie close to 1 or class 1. Otherwise, we can say that if b is negative, so if b is greater than 0, so these points, there is a higher chance that they will approach to 1. Okay. And if b is less than 0, there are higher chances for our data point to lie close to class 0. So your b is negative to the left of origin, so it is most probably tending to 0. Okay, like this. So here you can say that b is equals to 0.5 is your threshold value, based on which you are separating the data point to their respective classes, which in this case is class 0 or class 1. So you can see that when b is greater than 0, your output variable is 1, otherwise it is 0 based on above discussion. So now let us come back to our original problem and see how we can apply logistic regression here. We can write this thing as b. So y is equals to a function of b, and b is m0 plus m1 x1 plus m2 x2 for binary classification case, where we have two classes. Okay. So for now, let us assume we applied the gradient descent algorithm on this, and we got the values for model parameters, which are m0, m1 and m2. So let us say we got the values of m0 as 0, m1 as 1 and m2 as -1. And then if we consider the case when b is greater than 0, so this entire expression is b. So let us consider the case when b is greater than 0. So case 1, when b is greater than 0, m0 plus m1 into x1 plus m2 into x2 is greater than 0. Now put the assumed values into this inequality. So we can say put these values into the inequality. So you will have 0 plus 1 into x1 minus 1 into x2 greater than 0. So x1 minus x2 is greater than 0. And if a point satisfies this inequality, we can say it belongs to class 1. That means y is equals to 1. Otherwise, if b is less than 0, then we will get x1 minus x2 less than 0, which means we can say that y is equals to 0 for this case and y is equals to 1 for this case, as we had seen in the previous diagram. So we can easily conclude that since the new unforeseen data point that we classify belongs, so this will be your line which will represent x1 equals to x2. Okay. If you go above this line, you will have x1 minus x2 greater than 0. And if you go below this line, you will have x1 minus x2 less than 0. Now, since this point, the new unforeseen data point that we are trying to classify belongs to this side of the line, which is below this line, below the main line. Therefore, it will go to the class of dollars. So this is also a dollar. So let me mark this with another color. So this point will also come out as a dollar. So this is how logistic regression helps in demarcating new data points into classes. So let us learn about the cost function in case of logistic regression. We had discussed about the cost function in case of linear regression, where I told you that cost function is your residual sum of squares, which we had discussed in great depth in the video on determining the coefficients or parameters in case of linear regression model, and we also implemented it practically. So the link for all the 3 videos pertaining to this can be found down below. Now in the case of logistic regression, our cost function is defined something like this. So it is minus y into log y cap minus 1 minus y log 1 minus y cap. Now here y is your actual value, which is discrete either 0 or 1, and y cap is your predicted value. So this is your predicted value, or you can say predicted class in case of classification. So this was all about the video on introduction to classification and the logistic regression algorithm. So if you liked the video, do give it a thumbs up, subscribe to the channel, share the video with your friends and colleagues, and I will see you guys in the very next video.